In this chapter, we've been talking about functions and where they are increasing or decreasing. That kind of information can tell you a lot about the behavior of a function and can potentially help you get a relatively accurate graph of your function if you draw it by hand. Of course, we can graph things a lot easier with technology, but if we didn't have that available to us, using calculus in order to find out where functions are increasing and decreasing is a very good tool. However, the concept of increasing and decreasing are not really enough. Let's take, for instance, two particular functions. We'll have f of x is equal to x squared, and g of x is equal to the square root of x. If we graph both these functions, and specifically I'm only going to graph x squared for non-negative numbers. I'm only going to look at the from 0 to infinity. Let's put this in a separate color. We have a graph like that. And for the square root of x, of course we can't put negative numbers in here. We have to start at 0. And we have something like that. These are both definitely increasing functions over the interval from 0 to infinity. But they have quite a different flavor to them. X squared starts out nearly horizontal. In fact, at 0, the derivative is 0. And it gets steeper the more x increases. Whereas for the square root of x, it starts out pretty steep, but flattens out over time. It definitely is less steep over here than it is over here. Basically, what we're seeing here is how the derivative actually changes over the course of the function. In the case of x squared, our derivative is increasing. If we look at the slopes of tangent lines, maybe we'll put those in, let's do orange. We have tangent lines over here that have one slope, and when we look at the tangent lines over here, make that a little bit better, something like that, it has a bigger slope. As we go on, the slopes get bigger. For square root of x, we actually start off with slopes that get smaller as we go along. You have a bigger slope over here than we had over here. We're going to give this idea a name. So let f be differentiable on an interval I. So since we're talking here about derivatives and slopes of tangent lines, we definitely need to be talking about a function that has a derivative. Technically, we can actually get a concept here without using derivatives, but there's not really too much point for us right now. So we have a function that's differentiable on some interval I. F is, we say, concave up. Or as the book likes to put it, concave upward. But usually I find people use concave up more than concave upward. I should say specifically concave up on the interval I if f prime, the derivative of f, is increasing. Of course, if it's decreasing, we say concave down or concave downward. And we refer to the property of a function of being concave up or concave down on various intervals, because we can definitely have a function that is concave up on one interval and concave down on another interval, but we refer to that whole idea as the concavity of f. So in this section, we will be looking for where the function is concave up or concave down, but we'll just phrase it as find the concavity of f. Now, since we actually define concavity in terms of increasing or decreasing, we can actually use the techniques that we had in 3.1, the techniques of calculus, to talk about how to find where these are actually increasing or decreasing, and therefore where the original function f is concave up or concave down. So if we want to see where's f concave up, we're asking where f prime is increasing, and f prime is increasing if the derivative of f prime is positive. Or in other words, because the derivative of a derivative is the second derivative, we say if the second derivative f double prime exists on the interval, then f is concave up, well, I should still say on I, if the second derivative is positive on I. And concave down on I if the second derivative is negative. Because if the derivative of the derivative is negative, that means the derivative is decreasing. And by our definition, that means that the original function is concave down. If we go back to our original examples, we can go ahead and look at the second derivatives of these to see exactly what's happening. So let's say with x squared, we take the derivative. Of course, x squared becomes 2x. And when we take the second derivative, just differentiating 2x again, we get 2. 2 is a positive number. So, in fact, the second derivative of x squared is always positive. So actually, if I had continued this over to the other side, it would be decreasing over here, but it would be concave up still. The derivatives, the slopes of our tangent lines, they start out negative, but they get less negative until they become 0 at our vertex, and then become positive and get more positive as we go on from there. But the entire time, the derivative is increasing. For the square root of x, which if we're going to differentiate this, we might as well turn this into x to the 1/2 power. Then we go ahead and differentiate this. G prime of x, we take that 1/2, bring it down, then reduce the power by 1, so 1/2 minus 1 is a negative 1/2. This is still positive, in fact, because we're only going to put positive numbers into x, so this part's definitely positive, and 1/2 doesn't change that. But when we take the second derivative, if we differentiate this again, we have to use the power rule again. That means this negative 1/2 gets pulled out as well. So the 1/2 times the negative 1/2 that we got from there gives us a negative 1/4. Subtracting 1 from our power now gives us a negative 3/2. Of course, the x to the negative 3/2 is going to be a positive number, but we have a negative in front of it. So this derivative is actually negative for every value of x, at least from 0 to infinity. And that's what controls our concavity, the fact that we have positive derivatives over here, while we have negative derivatives over here. Or I should say second derivatives. Positive second derivatives over here, negative second derivatives over here. So finding the concavity of a function is going to actually be very similar to how we found increasing and decreasing, because all we're doing is taking the second derivative instead of the first derivative, but we're still asking where is the positive, where is it negative. And so we're going to have exactly the same kind of problem where our solution was basically to find out for increasing and decreasing, we found out where the derivative doesn't exist or where it is equal to 0. We're going to do the exact same here for concavity, except we're going to use the second derivative instead. And then we'll make a number line and take test points the same way that we did before. And we'll just go through some examples and get more used to it through the examples. But I do want to first give a name to the points where the concavity actually changes. Just like we had critical points when it came to increasing and decreasing. Remember, a critical point where the derivative equals 0 or the derivative doesn't exist. Just kind of a very brief definition there. We're going to come up with a similar kind of name for talking about concavity. We're going to define what we call an inflection point. Again, this is what I'm used to actually calling it, so I'll probably continue calling it an inflection point. The book, for some reason, is calling it a point of inflection. But the important thing is the inflection name. We don't use that for anything else. An inflection point is a point on the graph of f where the concavity changes. Basically, the concavity either goes from being concave up to concave down, or vice versa. It goes from concave down to concave up. But the concavity actually has to change at that point. Just like with critical points, these inflection points will only happen when the second derivative equals 0 or the second derivative doesn't exist. But unlike with critical points, where we grouped up everything that satisfied one of those two conditions and called it a critical point, we're only looking at ones where we actually do have a change in concavity. It is possible to satisfy one of these two conditions and not actually be an inflection point. This is kind of, if it had been up to me, I would have probably, just for the sake of having them similar, I would have just gone ahead and called any one that satisfied either one of these conditions an inflection point, and then talk about more specifically when the different types of inflection points, but that's not how it's been defined. So we're specifically going to be looking for inflection points by looking at these two conditions, and then we'll actually go and see whether or not we do actually have an inflection point. We'll see how that goes through our examples. Let's start with problem 14. Here we're given a function. F of x is negative 4x cubed minus 8x squared plus 32. Just like with when we were dealing with increasing, decreasing, and looking for extrema, basically what we've been doing throughout this chapter so far, I'm also going to identify what the domain is so that I can actually use that idea later on. Now this is just a polynomial, it's a cubic, so its domain is going to be everything anyways. So in this particular case, that's not too useful, but it's always a good idea to have that in the back of your mind somewhere, what the domain of the function actually is. Our question here, if I read the directions, discuss the concavity of the graph of the function and find the points of inflection. So we've defined these new concepts. We want to identify them for this particular function. Of course, the first thing we need to do is find the second derivative. And all I have to do there is take the derivative twice. So I differentiate one time. So negative 4x cubed becomes a negative 12x squared. I brought that 3 down, combined it with the 4. Here I bring the 2 down, combined with the 8. I get a minus 16x. And the plus 32 actually goes away. If I wanted to find where it's increasing or decreasing, I go ahead and find critical points and all that directly from here, but that's not what we're being asked for, so we differentiate it again. This time we bring the 2 down, combine with the 12, get a negative 24x. This one just becomes a minus 16. And now we're at, excuse me. Now our question is, where is this equal to 0, or where does this not exist? Now, of course, it is just a polynomial. It's, in fact, a linear function, so it always exists. We don't have to worry about that part of it, but we are going to have to set it equal to 0. Where does that equal 0? Well, it's easy enough to solve it. We'll go ahead and bring the 16 over, divide by 24. Of course, we can go ahead and simplify this. So both the top and bottom are divisible by 8. So we get a negative 2/3. And now I'm going to go ahead and make a number line for the second derivative. So I'm going to make a number line. I'm going to put on the negative 2/3. When we're actually dealing with these number lines, we've been looking at number lines for the first derivative before. And since we only had one type of number line there, I wasn't really putting any qualifiers on it. Here, because I'm specifically looking at the second derivative, I'm actually going to go ahead and label my graph here saying f double prime to note that I am specifically focusing on the second derivative here. This will actually be useful in some later sections where you might actually look for both stuff for the first derivative and for the second derivative. We're going to basically, I mentioned before that this kind of stuff can be useful for graphing a function by hand. We're going to actually do that eventually, and we're going to make use of every piece of information that we've been building up so far throughout this chapter. So from this point forward, I'm going to start labeling my number lines to tell me which function I'm actually using for that particular number line. This is specifically the one for our second derivative. Alright, so we have two intervals. We have from negative infinity to negative 2/3, and then we have from negative 2/3 to infinity. I need to take a test point from each of those intervals, just like we've been doing so far. And then I'm going to plug them specifically into my second derivative. Well, the easiest one from negative 2/3 to infinity, we can just go ahead and pick 0. 0's over here. So we might as well plug that into our second derivative. Of course, the negative 24x goes away, and we just left with a negative 16. So the derivative here is actually a negative value. There's second derivative. Now, the second derivative is negative from negative 2/3 to infinity. On the other side, let's go ahead and pick negative 1. If we plug negative 1 in here, the negative 24x becomes a positive 24, but then we subtract 16 from it, but we're still left with a positive 8. So the second derivative is positive on this part. So we can say right now, f is concave up. Concave up specifically where the second derivative is positive. So from negative infinity to negative 2/3. It's concave down where the second derivative is negative, so from negative 2/3 to positive infinity. And if we want to talk about the inflection points, now negative 2/3 is the only possible place there could be an inflection point, and since it did actually change from being concave up to concave down, since there is a change in concavity, there will be an inflection point at negative 2/3. But specifically, the inflection point is the point on the graph, so we need the y value as well. So it's at negative 2/3, but it has a y value if you plug negative 2/3 into the original function. And I did this off to the side, so it's not something I just did right in my head. It's 800 over 27. Fun little y value there. Let's go ahead and actually graph this. Alright, so our function was negative 4x cubed minus 8x squared plus 32. And it kind of looks like it's way off the screen. Things are just really big. It actually is above 30 when it actually turns. Or I can go ahead and scale it like that. That'll be a little bit better. Now you can see there's a relative minimum over here, relative maximum over here. That looks like it's probably at 0. We weren't actually asked to identify those, but we could have. But we were asked to go ahead and find that inflection point. So remember we had the x value of negative 2/3, we had a y value of 800 over 27, and we get a point right here in the middle. And what we're saying is that from negative infinity till we get to negative 2/3 is concave up. Notice here, if we think about the slopes of tangent lines, they start out very negative, but they get less negative as you go until we reach this relative minimum, and then they get more positive until we get to this point here. After that, the slopes of the tangent lines actually get smaller, and they go back to 0 before becoming very negative as we go on from that point forward. So we're definitely concave up over here and concave down over here. Always like to think of it as concave up has kind of a cup shape to it. Think of something like x squared. Think of that kind of a shape. Now, if it doesn't actually bottom out somewhere, you might only see part of this, and you'll have to kind of imagine what would happen if it did finish up the cup. But that's always the kind of idea that I like to have in mind. The concave down, I like to say it has a cap shape to it. It's like negative x squared. Think of the way that it opens up to as the direction it's going. So this is opening upward, this is opening downward. However you like to remember it is up to you. That's what I like to do. Next, let's look at problem 18. Here we have another function. G of x is equal to 2x to the fourth minus 8x cubed plus 12x squared plus 12x. Of course, this is another polynomial, so if we want to talk about its domain, this is going to be everything. It'll be a little bit more relevant later on. Go ahead and take the derivative of this, because we're asking the same question, what is the concavity of this and where are the points of inflection? So we're going to start out the same way of trying to find that second derivative. Differentiate this, we get that 2 times the 4, get an 8, and the 4 becomes a 3. Here we take the 3 down, so we get a minus 24 times x to the second power. Here we get to pull down the 2, so we get another 24, just times x this time. Finally, 12x becomes a 12. Now this is actually a case where finding the critical points would be rather difficult. If you set this equal to 0, this is not a very pretty thing to try to solve. It is possible to solve it. It's not very straightforward, though. You have to know how to deal with cubics. And hopefully that would come out to be nice, but I think it doesn't in this particular case. But since we're not actually looking for the critical points, we're going to go ahead and take the derivative again. So this 8 times 3, we get a 24 times x squared. Here we get a minus 48 times x, and a plus 24. The 12 goes away. And what's really nice here is we can go ahead and pull out a 24. We're left with an x squared minus 2x plus 1. And in fact, this is the square of x minus 1. So we can actually simplify our expression quite a bit. But the point here is that when we want to set this equal to 0, because that's where we're going to find the inflection points, or potential inflection points. If we set this equal to 0, normally we go ahead and just set this equal to 0 and try to factor it, but I've already actually done that. 24 isn't going to change anything. The x minus 1, though, is only going to be 0 when x is equal to 1. So x equals 1 is my only inflection point. Or, well, I shouldn't say inflection point yet, because I don't know if it's going to be an inflection point. It's possible that it won't be. But it is going to be the only number that I'm going to put on my number line. And that's the important thing here. Again, I'm going to go ahead and label this. This is the number line for g double prime. I need to identify whether or not the second derivative is positive or negative on these two intervals. I'll go ahead and take different test points. From negative infinity to 1, I can go ahead and take 0. Definitely an easy number to pick there. If I put 0 into this expression here, of course, the 24x squared and the minus 48x, those both become 0. We're just left with this 24. For 1 to infinity, I'll just pick the next integer of 2, and I'm going to go ahead and plug that in there. Now, 2 would actually be a little bit tricky to plug into this. You'd have to multiply 24 by 4 and all that kind of stuff. I'm actually going to go ahead and plug it into this expression here. We have 2 minus 1 gives us 1. Of course, 1 squared is just 1. And we just have 24 times 1. So we just get 24. Basically, in both cases, we got a positive number. We actually have positive numbers on both sides of this. So we can say that we're concave up from negative infinity to 1 and from 1 to infinity. And just like with increasing and decreasing, we can't immediately combine these, but it will actually be the case in this particular example that we can combine those into a single minus infinity to infinity. Basically, this function is actually going to be concave up everywhere. And it also means that we don't have an inflection point. There is no inflection point at 1 because the concavity did not actually change. Now let's actually take a look at this particular function and see why the concavity was the way it was. So remember, our function was 2 times x to the 4th minus 8x cubed plus 12x squared plus 12x. We get this function here. If we go ahead and actually shrink things a little bit, maybe you can get a better idea of what the shape of this really is. So let's even go ahead and move it downwards. So it is kind of a cup shape. It's got a little bit of character to it over here, but it never does actually have a cap shape to it at any point whatsoever. When we are at x equals 1, that was not what I wanted. Took out my f. There we go. So at x equals 1, we do actually have a little bit of a... That's where the character actually kind of happens. Our tangent line here does become kind of... I guess the way you might put it is that the graph kind of flattens out there. If we actually looked at tangent lines here, these slopes are increasing as we go, but they kind of slow down and stop increasing quite as much before starting to increase again. So it's kind of it just kind of flattens out. But the point is, it never actually stops being concave up. Technically, the slopes never stop increasing, even at that point. They are just kind of increasing through that point. They just kind of really slow down their increase. Alright, one more example for this video. We're going to look at problem 20. Here we have a function, f of x. It's x minus 1 cubed times x minus 5. Of course, this is another polynomial, even though it's not expanded. It is actually factored out for us. But since it's a polynomial, its domain is everything. Basically, they didn't give me anything other than polynomials for this section, for these collection of problems. So we're just left with things that have domain everything. We're going to go ahead and take its derivative. Now, I don't want to go ahead and expand this whole thing out, and in fact, there are some tricks that we can use in order to simplify our result by not expanding it out first. I'm going to go ahead and use the product rule, and I'm also going to have to use the chain rule or the general power rule. So I take the derivative of this first factor here that includes the cube here. We have something to the third power. I'm going to take 3 times that same thing to the second power times the derivative of the inside. Well, the derivative of x minus 1 is just 1. So actually, I don't even have to multiply by anything there. But I do need to multiply by the other factor as it already is. So that's the first term, is 3x minus 1 squared times x minus 5. Now I'm going to leave the first factor alone. Just going to leave the x minus 1 cubed alone. And I'm going to multiply by the derivative of the second factor. Well, the derivative of x minus 5 is also 1. So actually, I don't even have to put anything there. And now, since we are trying to find the concavity of this thing, I would have to go ahead and differentiate again. But that means I would have two general power rules. I'd have another product rule. How about we simplify this first? and save us a little bit of work in taking the next derivative. Basically, the idea I'm going to use is that I have 2 copies of x minus 1 here and 3 copies here. How about I pull out 2 copies from both of these terms? So essentially, I'll have an x minus 1 squared, but from here, I've already taken out the x minus 1 squared. I'm left with the 3 times x minus 5. Here, I've taken out 2 copies of x minus 1, and I'm left with a single copy of x minus 1. So I'm just factoring out something. What I have left in here is actually a linear thing. I can combine like terms. I have a 3x, I have a plus x over here. I have a minus 15 and a minus 1. So 3x plus x gives me a 4x, and negative 15 minus 1 gives me a minus 16. And in fact, things actually work out pretty nicely. Everything has a multiple of 4. So I'm even going to go ahead and pull that 4 out of that second factor. They'll just turn that into an x minus 4. So actually, my derivative looks very similar to my original function, which is kind of nifty. When I take the second derivative, I'm essentially going to do the exact same thing I did up here, except now I have a 4 that's going to stick around. And then instead of x minus 5, I have x minus 4, and I have a square instead of a cube. But the process is exactly the same. I'm going to use the product rule, and I'm also going to use the general power rule for the square. So I start with this part. Of course, I have to bring down the 2, and I already have the 4, so I have an 8 now. Times x minus 1 times the derivative of x minus 1, which is, of course, is just a 1, so I don't need that. And then I need to multiply by my second factor, this x minus 4. Then I add to that what I get when I leave this first part alone. I have to include that 4, by the way. So I have 4 times x minus 1 squared times the derivative of my second factor. Derivative of x minus 4 is, again, just 1. So actually, I don't really need to write that one either. And then I think, well, I want to set this equal to 0. How about I simplify what this one looks like too? So I'm actually going to do a very similar process to what I did up here. So this is maybe a little bit time consuming, some of this algebra, but it will be helpful overall. Essentially, I'm going to go ahead and pull out so everything has a 4 in it already. Both of them have an x minus 1 in them, so I'm going to pull the 4 and the x minus 1 out. This first part still has a 2 from that 8 and an x minus 4. And then from over here, I've already taken out the 4 and one of the x minus 1s, and I'm left with a single x minus 1. Then I'll go ahead and simplify what we have in here. We have a 2x and an x, so we get a 3x. Then we also have a negative 8 and a minus 1. That gives me a negative 9. And in fact, I can even pull out a 3. So I get a 12 times x minus 1 times x minus 3. So a good amount of work there, I admit, but it's going to pay off. Because at this point, we really don't even have to do much. If I set this, well, first of all, obviously the second derivative always exists because it is still a polynomial, but it's only ever equal to 0 if x is 1 or x is 3. We've already done the factoring that we needed to solve that problem. So f double prime of x equals 0 implies that x is equal to 1 or 3. And our number line for f double prime, go ahead and just put those on there. Now I do need to go ahead and use my formula here to take some test points. So I just copied over my second derivative, the simplified version of it at least. For my different intervals, I can go ahead and take 0 for negative infinity to 1. I can take 2 for 1 to 3. And I'm going to take 4 for 3 to infinity. So I'm just going to plug those values into my second derivative. For 0, I have 12. And then when I plug 0 in here, I get a negative 1. And here I get a negative 3. The negatives actually cancel each other out. And we're left with a positive 36. go ahead and put a plus sign over here. For 2, I have a 12. 2 minus 1 gives me a 1. 2 minus 3 gives me a negative 1. This time we have a positive and a negative, so we're left with a negative 12. So we have put a negative sign there. Finally, for 4, we still have the 12. This time 4 minus 1 is a 3. 4 minus 3 is a 1. We actually have no negatives in there at all. We get a positive 36 again. So we get a plus sign there. So we have our original function was concave up from negative infinity to 1 and from 3 to infinity, because those are the places where we have a plus sign. It's concave down from 1 to 3, because that's where we have a minus sign. We actually have 2 inflection points here, because we do have, at 1 it does change from being concave up to being concave down. At 3 it goes from being concave down to concave up. There is a change in our concavity. So we have 2 inflection points. So we have a point at 1, we have a point at 3. We technically do need to find those y values, so we're going to have to take 1 and 3 and plug them back into our original function. When we plug 1 in there, obviously this first factor becomes a 0, so actually that part is actually relatively simple. Plugging in 3 is not going to be quite as nice. Here we're going to have 3 minus 1, or 2 cubed, but then we'll have a 3 minus 5, which is a negative 2. So 8 times negative 2 gives me a negative 16. And those are our 2 inflection points. If we go ahead and graph this function, so we have x minus 1 cubed times x minus 5. We have this particular curve here. Maybe I'll go ahead and shrink the y-axis again. I'm going to go ahead and plot my 2 points that I found, my inflection points. Actually, accidentally typed 0, 0. It should be 1, 0. It does have an inflection point here, and it has an inflection point at 3, negative 16. So here, we can, if we think about our slopes of our tangent lines, they start out very negative. They get less and less negative until we get to this point. It's definitely concave up here. It kind of looks like half of a parabola if we want to think of that way. It's not exactly, but it's kind of got that character to it. At A, it switches and it looks like now we're following the half of a parabola that's pointed downwards instead. And it's concave down. But then at B, it actually switches back to being concave up. It definitely has that cup shape to it again. And from that point on, it just continues that trend. So that's the idea that we have going forward. So hopefully this gives you an idea of what concavity means, what the different shapes, how that actually corresponds to shapes of the graph. In our next video, we're going to actually discuss another consequence of concavity that actually will apply to some problems we've already seen, but it will give us a new technique for actually working with those. So I'll meet you in that video.